Hello everyone, welcome back to quantum computing with Qiskit. So this is episode 2. We're going to continue off of last episode 1. Kind of think of it as like part 2 or episode 2. So we're going to go back into Jupyter Notebook and basically pick up from where we left off. So in the last video, as Jupyter loads, we were able to say, let's play around with 2 qubits. And right now, what we're saying is manipulate these qubits according to some rules, and let's see what the probability that they are 0, 1, or superposition. So right now, we're just working with probability. So we go into top. That for is and all right. All right. So episode 1, we drew a circuit with 2 qubits and 2 regular bits, and we used a NOT gate and a control NOT to manipulate the qubits. So last time I showed you the function of how to see the simulations and quantum computers that are available. So we're going to rerun the load account. Let that run. Take a while. And then I'm going to run to see what simulators are open or computers are open and which one to choose. Remember, you don't need matplotlib inline command if you're not in Jupyter Notebook. But you will always need ibmq.load account, load your credentials, and send commands to the IBM quantum computers. Sometimes it's slow, sometimes it's long, like this. Alright, so now we can go and see which are open. Alright, so it looks like London has 0 queued and 5 qubits, so that's what we're going to use today for the shortest time. And yeah. So to recap, we created a circuit with 2 qubits. We said make the second qubit 1, make the first qubit 1 and the second qubit a 1 if the first qubit is a 1. So now they should both be 1, 1. And we said measure, we draw the circuit, and then ran the job in the quantum computer with this command. And from Qiskit.visualization, we plotted it, and we know the qubits should be 1, 1, and we see that's why it has the highest probability. Yeah. So, with that being said, we had 1, 1, which is what we were after, yet we got more than just 1, 1. You see we had 1, 0, 0, 1, and 0, 0. So quantum computers are very delicate, especially right now. They're kind of in their infancy, not, kind of. And there's things like quantum noise that mean basically their predictions can be wrong. And so we don't know. There's a small chance that they could not be what we want them to be. But now today we're going to play around with some of the simulators. So for faster runs, we can change instead of like IBM Vigo like we did last time. Qiskit actually comes with simulations where we run the code and it gives us predictions as if it ran in a quantum computer, but it is not as accurate as you'll see. So let's change our circuit. So we're going to say backend, create an object called backend, set it equal to provider dot get underscore backend, and we're going to say IBMQ, sorry, in lowercase, IBMQ underscore London. Because remember, that had 0 Qs. And we're going to create our circuit. So we're going to use a height mar gate. So it puts whatever qubit we put into it takes a qubit and puts it in superposition, and we see what the qubit is both, depending on how many shots we. Oh man, that isn't that good. We'll see in a bit. All right. So circuit equal to q dot quantum circuit in all capital 2, 2. So remember, we want 2 qubits and we want 2 corresponding regular bits. So we're going to create the HMAR. So we say circuit.h parentheses 0. And then we're going to say circuit.cx for that control not, comma 0. And then, actually, let me make sure that is the control not. CX was, yeah, it's the control not. It changes the second qubit if the first one is 1. So the height mar gate puts a qubit into superposition to where it's both. I believe so. All right, and then we create circuit.measure parentheses brackets 0, 1, comma bracket 0, 1. So we want the qubits to either be 0, 1 and the regular bits to be 0, 1. And then we draw our circuit. And so we have the height mar gate, we have the control not, and we have our measurements. So now we're going to execute the job. What actually are the bits of the values that are returned? And we can take shots that basically are like more predictions to see what it actually is, because we don't know. The computer is just guessing. So we create an object called job, set it equal to q.execute parentheses circuit, comma backend equal to backend, and comma shots equal to 500. I believe the more shots you take, the more accurate it becomes. So you then say job underscore monitor job. Job underscore monitor. Alright, so I need to. I'm going to rerun the command that says from Qiskit tool monitor import job monitor. Alright, back. So from qiskit.tools.monitor import job monitor. Should be all we need to run this. Job is being validated because there was no line, so it's just us. Dude, what? I thought IBM was, or London was free to go. Alright, whatever. Wait a bit. Alright, we're only second in line. So this function is actually really cool because it'll always list out, without having to go to IBM's website navigator every time to see what computers are open. So we just wait until it is ready. Alright, job is actively running. Job has successfully run. Alright. London has 2 queues. 5 queues. London's still pretty fast. Alright, so it has run. Now we can print out our results. So we say create an object called result, set it equal to job.result, and parentheses. Then we create an object called counts, set it equal to result.get underscore counts, parentheses circuit. Then we say plot underscore histogram, parentheses brackets counts. Plot histogram is not defined. Okay, go back. from Qiskit, import that. Come back and do that. So for this, you say from Qiskit.visualization, import plot histogram, from matplotlib, import style, style.use dark background, and we say result equal to job result counts histogram. Alright, so we see we get 0, 0, and 1, 1 because it was both. So we almost kind of got 50-50, 50% chance that it's 0, 0, and 1, 1 because remember, superposition is both 0 and 1, and we told the control gate, or well, the control gate says if it's 1, flip it to 0, or sorry, if it's 1, flip the second qubit to 1, and because it's in superposition, it should, I believe, flip it to 1. Yeah, so we are using a NOT gate, which means it'll only flip the second bit so long as the first bit is a 1, and in some cases it did, or it thinks it will. And so that was messing around with some superposition. It's a little crazy, but it's still pretty cool. So now I get to actually the simulator framework. So we can import a framework from Qiskit. So we say from Qiskit, import AIR, capital A-E-R. And so this is the thing that allows us to get some of the simulators. So we create an object called sim_backend, set it equal to air.get_backend, parentheses, in quotes, UASM_simulator, all in lowercase. And we create a for loop. We say for backend in air.get_backend, say parentheses, backends, colon, print, backend. Air provider, no object, get sim backend equal air.get end cosm simulator for back and back. He's not liking that. Air provider object has no option. So air.get_back get back print backend. And it should print out cosm. From Qiskit, import air. Create an object called sim_backend equal to air.get_backend cosm simulate. That should be what the original one. Simulate. And we say for backend dot. Oh, sorry, I didn't even see it. It's just air.backend. There you go. Sorry about that. And we see we have quasm_simulator, state vector simulator, unitary simulator, and pulse simulator. So quasm simulator is one of the simulators that's actually in the cloud. That's the first one listed in IBM, and it acts as if it had 1 qubit, but it's actually just a regular computer that's faster. State vector, unitary, and pulse, these are actually all simulators. They don't actually run in the cloud. They run on your machine, but you will see that so these will yield very close results, but not entirely accurate. So Quasm Simulator works like normal, shows us results based on shots. Stata shows run once, but shows all possible results, and it takes a lot of computational power. And yeah, so that's kind of the takeaway. I don't know what the other two are just. And then we say job. Let's play around with the first with the Quasm Simulator. So we're going to create a job, set it equal to q.execute parentheses circuit comma backend equal to sim underscore backend comma shots equal to 500, and we're going to monitor the job monitor job, and we're going to say result equal to job.result parentheses, and we're going to say counts is equal to result.get counts, and we're going to pass in our circuit. And we're going to say plot underscore histogram parentheses brackets. So remember, we're just using the last circuit we created where we had the HMAR superposition, we had the control knot, and our measure. Run. So this is sending info to a computer, I believe, in the cloud that's just a regular computer server, basically, and it returns info. But you see, we get no background noise, so there's no possibility that it failed, which it could, even if we actually ran it in a quantum computer, it could fail. So you see we get the properties that where it was 50-50 because the first bit, qubit, was in superposition, so it's 1 and 0, and it should affect the second qubit. But you see how it's very similar to this one, except there are no background noise. So it's technically actually inaccurate, but it worked as if in a quantum computer. It gave us like a simulation. And yeah, so that was episode 2, kind of a shorter one. But that's kind of our intro to IBM. And thank you for joining me.